Well, sorry I couldn't be with you this afternoon. I took a half personnel day because Nora and Kieran are running in what's called the Race Around Webster. They go to Webster and Urbandale. And we always go, my wife and I take the afternoon off to go watch them do their race. And Nora's really competitive about it. She's currently the fastest girl as far as distance running is in the school. So they run a 5K. And she has this one girl she really wants to be able to beat. So they're both really fast. So she's going to do that, and it'll be a lot of fun. It'll drive me crazy, make me nervous like nobody's business, but it'll be fun. So here's what you should have in your hands. You've got this. It says Assessment A on there, but we're going to take this one together. We're going to do it as kind of a recap and a review. Ultimately, you do have to do an assessment almost similar to this, just as kind of a review of old ideas, because you know this is from a long time ago, but it's kind of a I want to cycle this back so that you don't forget it before we hit that midterm. We don't want to hit you blindsided at the midterm. So now, how do we deal with these? Here's these rational functions, and things that we need to know about them are listed in the grid below, and we're just going to talk about how you go find those again. I'll start you off and then let you finish the rest, and then I can kind of show up. I'll post a key to the Google Classroom so you can kind of see how that goes. But this will just get you rolling. So make sure you got these in your hand, you're ready to roll. The things you first look at are vertical asymptotes. They're kind of set in order. And vertical asymptotes are because there are these vertical gaps in your graph that look like lines where the graph snuggles up against it. One other thing about an asymptote you want to be sure to note is that it's a place your graph approaches. They literally squeeze up against it. So one misconception we've had on some previous tests, and this is just, you don't need to write this, but if I have a parabola and I graph it, some of you are saying, hey, there's a horizontal asymptote at 0. There isn't. There's no asymptote in a parabola because the graph, at the x squared graph there, is not hugging anything. An asymptote is if a graph snuggles up against it and it gets closer and closer and closer to a line, but never actually touches it. So it's a snuggling feature. So I'm going to undo those real fast and get that off the page. Zip, 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 zip. And let's get back to work. Okay, so vertical asymptotes are where the denominator is equal to 0. It's whenever you divide by 0. That's the big illegal move in mathematics. So if you try and factor that denominator, I know you're thinking, oh, 2 and 3, negative 3 and 2 would work, but it's a positive 6, so this one doesn't factor. So in order to find the vertical asymptotes, it's all about finding the zeros of the denominator, our possible vertical asymptotes. So we're going to solve this with the quadratic formula. We're going to set it equal to 0, and we're going to end up with the quadratic formula, so you get the opposite of b plus or minus the square root b squared minus 4ac, all the good stuff that I'm sure is quite easy for you at this stage. It should be. And over 2a. So there's your quadratic equation to solve for x's that would be zeros. And if you complete this, we don't have to go all the way because you're going to notice something, right? You're going to notice that if I finish this off, that's the square root of negative 23 all over 2. And that's a problem. Those are imaginaries. And so with the square root of a negative, an imaginary number pops up. And the thing about vertical asymptotes and zeros and all that, all the things that we do with rational functions are about finding real values. And so these are imaginary, and therefore with this, there's no vertical asymptotes. There's no real values of x that cause division by 0. So there's none. And I'm going to write in here a little special note. The denominator has zeros, but they're not real zeros. So the denominator has no real zeros. That's what we look for vertical asymptotes. Barring the idea of a hole, which we'll get to a little bit later. Now, horizontal asymptotes, you have somewhere got to tuck this definition away, because horizontal asymptotes are what all of us forget the most. We need to remember that there's 3 different conditions that occur. You can have somewhere, you have a rational function. It's all about rational functions. Okay, so excuse me. So it's 3x squared plus, and then if I put in there x plus 2, and then the denominator, if it has the same lead, same degree, the same highest power, no matter what it looks like, you do the ratio of the lead coefficients for your horizontal asymptote. Okay, so in that case it's 3/5. So yeah, all right, in that case y equals 3/5 is my horizontal asymptote, my ha, so to speak. Okay, so that's what I got right there. If it's bottom heavy, higher degree in the bottom, so I can do something similar, 3x squared plus x, oops, I keep hitting that edge, over like, let's do 5x to the 4th plus 2x, etc. If the degree on bottom is higher than the degree on top, then it's always a horizontal asymptote of y equals 0. So that's your other option. Now the last final option is, if you think of it, if it has the same degree top and bottom, higher degree in the bottom, the only other option we have is a higher degree on top, and there is no horizontal asymptote in that condition. So if I do 5x to the 4th plus 3x, etc., over 10x to the 3rd plus 2, something like that, this is higher degree on top, and there is no horizontal asymptote. That's the other condition. So those are the 3 places. You want to, at this point, well, what we talked about yesterday is that this is something we've seen for a long time in multiple classes, and it doesn't stick, and that's normal. So you're at that stage now where you have to think, well, just doing it and writing it down isn't sticking. I have to find a way to make sense of it. You have to start reasoning about what a horizontal asymptote is, and we hopefully will in these problems as we continue through them. I'm not there today with you guys. In the other class, of course, I pestered with all kinds of funny ideas, but you guys are going to sit there and just do the best you can to think through it and say, well, why? What's going on? Why? What is it about horizontal asymptotes I need to know? And the big concept is, if we can keep that in mind, a horizontal asymptote is a value your graph approaches at very large values of x. When you zoom out and you see this graph leveling off at a certain height, that's what a horizontal asymptote is. It's where your graph goes. It's the value at large values of x, and that's what we're interested in. Maybe you can interpret that in other ways, but it's about getting extreme values of x. And if I think of the ratio one that everybody seems to remember the most, when I think of this being like billions that I put in for x, 3 billion over 5 billion is basically 3/5. You're saying for large values of x. And we tend to ignore these littler things back here, because when it comes to a billion squared over a billion squared, that's so much bigger than the other stuff, we just ignore it. So ultimately we just get the ratio of 3/5. Okay, so back to work. We're going to put that in there. Which condition do we have here? So let's go look at ours. Our problem is x on top to the first, x squared on the bottom. That's bottom heavy. So we know right away that it's y equals 0, higher degree on the bottom. Okay, and then when it comes to slant asymptotes can be found, and it's actually that's a poor definition. It's actually really, we should just be saying end behavior. One of the ways we can determine the end behavior is by long division. And so if I long divide this problem, x plus 2 divided by x squared minus x plus 2, x squared minus x plus 6, and you try and long divide that, the quotient ends up being your slant asymptotes. So I need to put that in there. The slant asymptote is the quotient from long division. Okay, that's what it is. And if you want to think of it more broadly, the long division, that quotient, just tells you the end behavior, what your graph does at the end. Even in this case, it does a nice job of that. How many times does x go into, did you notice something I did on this one? I did it in the other class too, and I'm doing it here for you guys on purpose. Did anyone balk at this? I hope you're kind of squirming in your seats or saying something out loud. Divided these backwards, right? We're taking x plus 2 divided by x squared minus x plus 6. We had a ton of fun second block talking about how that went backward. So if you look at this, it's still okay, the idea of the quotient. But I wanted to give you guys the same experience. Be careful how you do your long division, because it's really easy to write them in backward. When you divide, the numerator goes inside, and outside it's x squared minus x plus 6. Okay. Yeah, you can ask him. I told him to make fun of me, and we had all kinds of fun with that. How many times does x squared go into x plus 2? Well, it doesn't. And in fact, remember I said the quotient is your slant asymptote? It goes in 0 times. But that's actually what I'd put in for my slant asymptote, which would be 0. The funny thing is that's actually 0. It's y equals 0, by the way, is your slant asymptote. That's the same as our horizontal asymptote. And actually, if you do long division, your quotient will always tell you the end behavior of your graph. Horizontal asymptotes, a flat line is just a particular kind of end behavior. So we've talked about that in the past. The quotient is your end behavior. So if you guys don't want to remember all the horizontal asymptote rules, you can actually just do long division every time. The quotient will give you the correct result. So it's kind of a way out from having to memorize that end behavior with horizontal asymptote stuff if you don't want to. But at the same time, it's also good to just really quickly be able to recognize, a particular problem and go, hey, that's bottom heavy, the horizontal asymptote's y equals 0. That's an important skill. But long division will do the trick as well. Turns out there's no holes. The question keeps coming up, what are holes? How do I know where they are? We all seem to struggle with what they are. As an example, an aside example, not one that's on this sheet, because it turns out there are no holes in any of these today. But if I gave you this rational function, I said, all right, let's look at this one. Are there any vertical asymptotes in this? And everybody's going to go, hey, look, x can't be 0. So you're going to say it must be a vertical asymptote at x equals 0. And you almost be right. Usually that's the case. The only thing different about this one is that algebraically, do you notice that those x's would cancel? Well, if those x's cancel, x still can't be 0. You still can't divide by 0. But instead of the graph having a vertical asymptote, in this situation when that canceling occurs, that it becomes a hole in the graph at 0. Same location. So I'll give you another example. When it cancels, that factor that creates your vertical asymptote, here's another example, not a problem on your sheet. Okay, here goes. If I did x minus 3 on top and x plus 2, and on the bottom I had x plus 2 again. Here's my other example. Usually I'd look at that and go, oh, look. Can't have negative 2. There must be a vertical asymptote at negative 2. But in this particular case, because it algebraically cancels, that factor cancels, instead of a vertical asymptote at negative 2, you actually have a hole in your graph at negative 2. It ends up looking like a line. Oops, undo that real fast. It looks like a line, x minus 3, but it has a hole at negative 2. That's something that we can talk about again more. This particular problem doesn't have, these 3 here don't have any holes in it, but that's the idea. It's like if you have a vertical asymptote, you wrote it in that vertical asymptote block there, but later found out algebraically that factor from your denominator cancels with the numerator, then you go, oh wait, that's actually a hole. You just kind of transfer it from one category to the other. Okay, back to our sheet. X-intercepts. X-intercepts are when you set y equal to 0. And for this that means the whole expression. You can think of the f of x function as being your y in a sense. So that's kind of how, or your output. You just set the whole thing equal to 0. And setting equal to 0, you may recognize in our old thinking, we could solve this by multiplying both sides by the denominator, but you'd end up taking, times 0 on the right, and it would cancel on the left. So you'd end up with just x plus 2 equal to 0. Or you might remember that if this is going to be 0, you really only have to think about the numerator being 0, because 0 divided by anything is 0. And that's how we kind of roll with these rational expressions. We just, finding where the whole function 0 is really just about setting the numerator equal to 0, because that will do. That'll make it 0. Solve it. Hey, negative 2. We have a y-intercept at x equals negative 2. Okay, I'm sorry, an x-intercept at negative 2. Y-intercept is the idea when you hit that vertical axis, you actually have to set x equal to 0. It's pretty easy to work with in your original function. So if you put zeros in for all your x's on our original function, so 0 plus 2 over 0 squared minus, if I can get my thing to work, so on top it's 0 plus 2 over 0 squared minus something 0, and then was it plus 6 at the end, plus 6? You end up with 2/6, which is 1/3. So your graph crosses the y-axis at 1/3. Okay, that's it. That's the process. Now we repeat this over and over again. Those are the big characteristics we need to know. So you want to repeat that down below. Again, I said there's no holes in these, so don't get too caught up in that. If you want to do slant asymptote, remember you're going to do long division. You can actually just do long division anytime to get your end behavior. Everything else should be relatively peach keen. Be careful on the third one. I know there's a whole slew of you that will fall for this. Don't forget x plus 1 quantity squared is x plus 1 times x plus 1. It is not, do not distribute that power in there. You need to make this x plus 1 times x plus 1. It probably would be helpful in this case for a lot of us to multiply that out and get x squared plus 2x plus 1. I'll let you do that because it kind of helps you see some of the things you need to see. But in its factored form, it's actually kind of nice too, because I bet some of you are like, ooh, I see a vertical asymptote at x equals -1. And you'd be right. All right, enough of those hints. On the flip side, some things to think about. This, you want to read very carefully about the context. X is the percent of the population being vaccinated. This whole function is about cost in millions of dollars. The questions say, give me an answer, but interpret. Means I want words telling me what you got. B, you can look at the graph. Just use tools that you think would help you answer this question. Just be smart like you are. The rest, answer well. You're going to turn this in before you go. Got to have this bad boy done before you head out the door today. And I will post some other work that you guys and the class can work on. There's the graph practice gateway. You want to get that filled in. You want to look at the key that's online and see if you can go getting that finished. And there's an additional worksheet that I have in here that gets you ready for tomorrow's work. So get ready to have some fun. A big hint, sorry, on this last one here, it might help in some cases for you guys to rewrite this, because I think what you might not notice is that there's a horizontal asymptote in this, but it might not be what you think, so watch out. But if I rewrite this function here with the -x out front instead of toward the back, this tends to help people notice some things on there. And quite frankly, I think you should, to help you out, do the same thing we did on the other page. Find the vertical asymptote, the horizontal asymptote, the x-intercepts, the y-intercepts. You want to find the Verhaltensintient, the whole thing, get it all, and that'll help you answer some of these questions. Hey, we'll meet up again tomorrow. Let's keep Nora, keep thinking about her, making sure she's fast today, and just has fun. I want to make sure she has fun. We'll see you guys soon.